So now let's review a big chunk of circuits, right? So circuits is when we apply a voltage, okay, across a circuit with resistors and capacitors, things like that. We have a flow of charge per unit time, right? And an amp is the units. It's coulomb per second here. And it's literally the rate at which the current flows, the rate at which the charge flows, right? So when you have a potential difference across a circuit, it has to flow. Now, it has to flow in a loop, right? So we'll get into the Kirchhoff rules, but a complete circuit has to start from a voltage source and then return back to the voltage source in a loop like that. Right now, current is the flow of charges. Now, by convention, because when they developed some of this math, they didn't know what the charges were. We know that electrons actually move, but positive current flows from higher voltage to lower voltage. It's as though we thought originally that the positive charges were moving, so by convention we still stick with that, but really it's the electrons moving in the opposite direction. So if current is flowing in this direction, then the electrons are flowing in this direction, okay, opposite the direction of the current. But just pretend fictitiously that it's positive charges moving. That's not what's physically happening, but it will work out the same way. But positive current flows from higher voltage to lower voltage. Now, the power dissipated across the element in the resistor is the voltage times the current. So we'll talk about power. Power being the current times the voltage across it. There's a couple of pieces of lab equipment we do here. An ammeter measures the current through a segment that passes through it. Has to be placed in series. If you place it in parallel, okay, like none of the current's going to go through it, right? So then it's never going to measure anything. Voltmeter is the potential difference between 2 points. It's generally placed in parallel, okay? If it's placed in series, then you're going to measure zero voltage drop because it's a voltmeter is like a wire, right? So, and then last is current density, which is kind of new for AP Physics C. They didn't really ask that many things about current density. But current density is the amount of current per area, and sometimes you have to set up an integral to find the total current. So they might give you, example, a current through cross-sectional area of a wire, and you have to figure out how much total current is flowing through it for some reason. Then you would use this integral setup. Okay, resistance is the most common circuit element we deal with, right? It has an ideal resistor follows Ohm's law, which is the voltage and current are proportional to each other, and that proportionality is called the resistance. The resistance is dependent on the resistivity, length, and cross-sectional area. So resistance is given by this equation here. That's where the resistivity is the property of the material, like what kind of metal it is, and then the length divided by the cross-sectional area. The power dissipated, we just talked about, was I times V. Now, one thing is, this is just a factoid you have to know, is that there is a temperature dependency on resistance. That is, the temperature, as the temperature increases, the resistance does increase a bit. So, that's just something to know. You don't have to know mathematically how that works or any equations related to that, but that's just a factoid. And in terms of the current, the electric field in a conductor. Now, okay, one thing I didn't keep in mind is when we are applying a voltage across it in a circuit, we are no longer in electrostatic condition where the electric field is zero. There is definitely an electric field. It's pushing the charges along. That's why the charges are moving. Okay, so the electric field is not zero anymore because it's not electrostatics. Electrostatics is when everything kind of settles, but in a circuit, we are applying a voltage and an electric field to cause the charges to move. And so the electric field is actually proportional resistivity times the current density. That's just something you can think of as a factoid. We could derive that, but just imagine this is really just telling you that there is an electric field and it's causing the current, right? Kirchhoff's laws, huge portion part of our analysis, all right? There's two kind of rules, the current law and the voltage law. Sometimes they're called loop rules because we are doing them as loops. Okay, the sum, well, at least for the voltage law, voltage loop. Okay, the current law is really just saying the current coming in has to equal the current leaving. Charge is not allowed to pool anywhere. Capacitors are kind of a little bit of an exception, but effectively we say like the current coming in and the current going out must be the same. Okay, that's like anytime you do circuit analysis, that always has to be true. There are no exceptions to this rule. Okay, currents going in equal the current leaving. Okay, so whenever you have a node or a branch of wires, then you have to remember that the current going in has to be current leaving. That means if there's just a single wire element, the current has to be continuous throughout here. It cannot change or decrease. Okay, so current, the amount of charge that's flowing, think of it like water flowing, think of it like traffic, right? Water, like when cars go into an intersection, they must leave the intersection. They're not allowed to just stick around in the intersection there. Okay, this is saying that charge doesn't build up anywhere. It's always flowing in and flowing out. The voltage law is the sum of the voltages in a loop have to add to zero. It's basically the voltage drops between any 2 points have to be the same regardless. And so the way you want to think about that is you're always going to have a positive and a negative, and you always want to think about in a circuit when we go through this is that when there are drops or when there are we'll go through several examples of this, but basically through these drops, these loops, the voltage just needs to add to zero. And anytime you go up, you go from negative to positive, you go up in voltage. Every time you go from positive, negative, you go down in voltage. And that sum, all the going ups and the going downs need to add to zero. Okay? And we'll go through some examples as we do there. We also sometimes like to simplify our analysis with series and parallel resistance, right? So if two resistors are in series, now how do we define them? Series resistors where they have the same current going through it. Okay, it doesn't mean that they're in a line. That's not really like if I do this in a line, these two are in series because they have the same current going through it. But if I do this, these are in a line, but they no longer have the same current going through it because there's a possible path for the current to separate. So these two are no longer in series because they don't share the same current going through it. Parallel resistors have the same voltage across them. What that means for parallel is that they have to, in effect, they have to be connected here on both sides like this. So these two are parallel because they share a connection by a wire on each side. Both sides have to be shared, not just one side or the other. So parallel doesn't necessarily mean that they're next to each other in parallel. It could look like this. Or actually, sorry, let me draw one. All three of these resistors here I'm drawing are in parallel, even though it doesn't look like it. They're parallel because they share a connection here on one side, and they share a connection by wire without anything interrupting them. By a wire connection, they share on both sides. So all three of those are parallel. And these are the formulas for series and parallel reduction. Now, why do we use them? We collapse resistors a lot of times in order, if we have a more complicated resistor network, we will sometimes collapse it so we can calculate the current coming out of the battery. Because you can then replace these three resistors with a single resistor, and that may allow you to solve for the current coming out of the battery. Okay? So that's kind of why we do that. Okay, so our problem-solving steps for resistor-only circuits, this is what we're going to do. We may combine parallel and series resistors. We want to draw the directions for the current for every resistor, every element. I should say call this an element, not device. Usually we'll have the current come from the battery voltage source and loop around. If you can't tell, so this is direction of the current. So if you can't tell, just make a guess about the direction of the current, and it's okay if it's wrong, because what will happen is if you solve it and get a negative number, it means the current was pointing the other direction. Okay, we want to draw positive and negative signs across the device. Now you need to follow the rules based on how you drew the currents in this one. For batteries and voltage sources, the positive is the longer side of the battery. So that means when you have something like this, this is the positive side of the battery, this is the negative side of the battery. Okay, for other components, put the positive side so the current flowing into it is the positive side. So for example, if I draw a resistor like this and I draw the current like this, then I want, and it's coming out of the battery, then I want to draw the positive convention like this, that the current is flowing from positive to negative, okay? So we want to draw the currents, then draw your positive and negative signs on each device element. For every resistor, if you know any of the two values, V, I, or R, so 2 out of 3, because V equals IR. For any resistor, if you know 2 of the 3 unknown values, the voltage, the current, the resistor, if you know 2 of them, you can solve for the third one. And you can apply KCL and KVL as needed until you can solve for the current and the voltage for every element in the circuit. So that's how we do the problem-solving steps for resistor circuits. Okay, then we might have capacitors. Okay, so similar to resistance, capacitors can either be in series or parallel. The equations are reversed. Parallel configuration means the same. Parallel capacitors have the same potential difference across them, which means that they share the same connections on the top and bottom. on each side. Parallel capacitance is you add, series capacitance you add reciprocal. So it reverses the rules for resistors and things. Things to keep in mind. For parallel capacitors, they have the same potential difference. For series capacitors, we don't say they necessarily have the same current, though. Although that's true, they have the same current because they're in series. The current can't go anywhere else. But they also end up having the same charge on them because of the same amount of current going through them. They end up with the same amount of charge. Okay. RC circuits is the combination of R and C circuits, and this is where it gets a little bit tricky. The voltage between the capacitor is dependent on the charge. Right? Q equals CV. Because charge takes time to flow, the voltage takes time to change. Right? So because the flow Q is the flow of the current, so the flow of charge is the current. So because that takes time, because current's not instant, the charge doesn't appear instantly. It takes time for the current to arrive, or it takes time for the charge to arrive. Then the voltage takes time to change. Okay? So there's kind of there's a few rules we look at. In steady state, there's no more charge flowing into the capacitor. The current is 0. So if a capacitor's been in a state for a long time, you can assume I equals 0 through the capacitor. Okay? The other thing is the voltage takes time to change. This rule here is really saying the voltage cannot change instantly. So that's an important part. So whenever a switch is thrown on these circuits, whatever the voltage was on the capacitor before the switch, right after you flip the switch, the voltage on the capacitor has to be the same value because the voltage cannot change instantly. It takes time for it to change. You generally can use KVL and KCL to set up a differential equation. This is one thing I've noticed is they do want you to know the equation, but a lot of the times they will not allow you to just solve for the voltage and current equation directly. You need to set up the differential equation and solve it. Okay, so we'll go through an exercise of doing that. The time constant, R times C, is how quickly the capacitor will charge or discharge in the state when it's transitioning, when the voltage is changing. Okay, so problem solving steps when you have RC circuits. You want to establish the initial state of the circuit, and you go back to looking at the resistor problem-solving steps. When things have settled for a long time, there's no current going through the capacitor. You solve for the voltage across the capacitor in this state, V0. Once the switch changes, the voltage across the capacitor does not change instantly, so it's still V0. Current is now allowed to flow into the capacitor. Now you solve when waiting a long time. After a long time, there's no longer any current going through the capacitor. The current through the capacitor is 0. That doesn't mean there's no current in the circuit. It just means through the capacitor specifically, there's no current. And you solve for the voltage across the capacitor, VF. Okay, the voltage across the capacitor will be a curve that starts at V0, like conceptually. And graphically, it'll start at V0 and go closer to VF. And the time constant is RC. It will be an exponential approaching it, right? And use Q equals CV if you need to know the charge across the capacitor at any given time. You may use KVL or KCL to set up the differential equation if you want to get the equation of the charge as a function of time. Okay, so let's go through a few problems now that we got the basic concepts down, but the big thing is how do you actually go about solving problems? So I have two air-filled capacitors with capacitance C and C over 3 are connected in parallel as shown. Parallel because they share a connection here and they share a connection here. The equivalent capacitance is C equivalent. A dielectric is inserted to the capacitor with capacitance C over 3, and the new equivalent capacitance is 2. What is the value of the dielectric constant? So this is a combination. So right now, CEQ, because these are parallel, is C plus C over 3. Right? They're parallel, so we add them up. That's 4/3 C. Once I add the dielectric constant, what happens is the capacitance is now going to turn to this. So now we know the new equivalent capacitance is once I put the dielectric constant, it's going to be C plus kappa C over 3. Because remember, the dielectric constant will increase that capacitance, right? So this is going to be, if you factor out a C, 1 plus kappa over 3. And that equals 2 times the equivalent, which is going to be 8/3 C. So the C's cancel here. And so you get 1 plus kappa over 3 is equal to 8/3. Kappa over 3, you subtract 1, is going to be, 5/3? So kappa has to be 5. Okay, so like that. All right, cylindrical wire segment with length 0.25 meters. So we have a cylindrical wire. Has a length L of 0.25 meters. Diameter is 3 times 10 to the negative 3. Dissipates energy at a rate of, this is the power, right? So the power is going to be I times V. is 6 times 10 to the negative 4 when the current is 0.5 in the wire segment. Okay, which the following is equivalent to the resistivity of the wire. Okay, so how is this all related? Well, here we can find the voltage, right? The voltage, because we know the current is 0.5, so I times V is this. We know the voltage across here. When we apply the voltage across here, we're going to get, 6 times 10 to the negative 4 divided by 0.5, which is going to be 12 times 10 to the negative 4 volts. Okay, now that is equal to I times R. So we can use that because now we know the voltage across here. We can, and we know the current. We know V over I is equal to the resistance itself, right? So that's 12 times 10 to the negative 4 divided by 0.5, right? And that's going to be 24 times 10 to the negative 4. Now that equals the resistance. In terms of the geometric shape and resistivity, that's equal to rho L over the A, right? So we want to solve for rho. So rho is going to be 24 times 10 to the negative 4 times the area divided by the length. Now, what is the length? The length is 0.25. The area is the cross-sectional area through here. So that is equal to the area of a circle, pi r squared. Remember, the r is half of this because that's the diameter. So you just put those numbers in together, plug that into there, and then you can solve it. So 24e negative 4 times 0.25 divided by this pi times 3e negative 3 divided by 2, and then square that. I get the resistivity is 84.8. Let's see if let me double check if I divided by 0.5. Then divide that by 0.5, and then times pi. Oh, I messed up the. Sorry. I messed up my calculation here. I get 6.8 times 10 to the negative 8. Okay, so I get A here. Yeah. Okay, cool. All right. Let's see. A junction, a circuit consists of 3 wires connected together. Which of the following diagrams could indicate the directions and magnitude of the currents in the 3 wire? Okay, so we have current. Remember, all the current going in has to equal the current leaving. So, for example, we have 2 going in and 8 leaving. This can't be true because I got 3 leaving and 5, because it just falls. Here I have 3 going in, 5 and 7 going out, right? So 3 going in and 7 going out. That's not KCL. Here, all of them are leaving. 3 is leaving to the right, 2 is leaving to the left. So I have none entering, and I have this thing is just creating current. That can't be true. So here I have 2 going in, 3 going in. So 5 going in, and then 5 leaving. So this one is good. Okay. All right. When a non-ideal battery is connected to a resistor with resistance R, as shown in the figure, the current is I. When the same non-ideal battery is connected to a resistor with resistance 3R as shown, the current in the circuit is I over 2. What is the internal resistance of the battery? Okay, this is fantastic. This is a good problem. You could do series collapsing. You don't have to do it. Let's just do it by KCL and KVL, just so you guys get a sense here. So, for example, we know it's I in this case. So we don't know what the battery volt. Okay, so let's first draw that we have the directions of the currents, right? That's the first thing we draw. We draw the currents. The currents are here, and the current comes out of the battery like this. So the current comes out of the battery here, comes out of here, goes into here. And we know those currents. That's like kind of a given quantity for us. Okay, now we want to assign our positive and negative symbols. So positive, the longer side for the battery is positive. And then the direction always goes from positive to negative like this. Okay? Now, can we calculate those voltage drops? Well, this one is I times R. This one is I times little r. And then this is the, we'll just call it V for the battery voltage. Okay, this is the same battery voltage here. This is the volt, because this is I over 2. It's 3R times I over 2. Right? Oops, let me just, which is going to be 3 halves IR. Right? So it's going to be 3 halves IR. And then this is going to be 1 half IR, I little r. Right? Cool. We want to know the internal resistance of the battery. So I have this relationship in terms of what the voltage drop is, but I really want to solve for that R there, right? That's like my goal. Now, let's look at our loop rule when we do this one. So if we start at a point and make a loop here, this guy's going to be going up V, then down IR, because you go from positive to negative, and then minus I times little r, that has to equal 0. So the voltage here has to be I times little r plus big R if you factor it out, which is what you would get if you combine those in series, right? This thing, do the same loop. We're going to go V, then minus 3 halves IR, then minus, drop here, 1 halves I times little r. That has to equal 0 as well. So then the voltage here has to be 3 halves IR plus 1 half IR. And again, this is the same voltage across the battery. If you factor out 1 half I, you get 3R plus little r. So those are going to be equal to each other. I times r plus little r is going to equal this, 1 half I 3r plus little r. Now it's just a math equation. The i's cancel. Good. We didn't have any i's in here. We didn't need to know what that was. And then go and multiply by 2. We get 2r plus 2 little r equals 3r plus little r. Move that over, you get r. Move that over, you get big R. They're just equal to each other. Okay? So that's the idea. Okay, so that is how you can do it. You can do it with series and parallel collapsing as well. Okay, but I want to show you I wanted to do that to illustrate that is the circuit analysis process for resistors. Okay, that is the process you follow. You can collapse them, sure. Okay, and that would have worked in this problem, but it doesn't work in all problems, which is why it's not always a thing you want to just automatically do. Okay, let's look at a few FRQs now. Circuit above, ideal battery of V0 is connected capacitor with capacitor Z0. Resistance R1, R2. R1 is bigger than R2. Switch is open, and the capacitor is initially uncharged. Uncharged means Q is 0, and that implies that the voltage on the capacitor is 0, because Q equals CV, right? If I know the charge, then I know the voltage, the relationship between them. The switch is closed at time t equals 0. On the axis below, sketch the charge Q on the capacitor as a function of time. Explicitly label any intercepts, asymptotes, maximum, minimal numerical values, or algebraic expressions as appropriate. Okay, so the charge is going to start at 0. And if you wait a long time, so we close it, so the charge doesn't appear immediately. If you wait a long time, the I through here is going to be 0. Okay, so there's no current going through this branch. So that means when we analyze our circuit, so now we're studying at, wait a long time. What we're studying here is we're saying, let's draw our current. So the currents are going to come out here and then go down through here and come back through here. But no current is going to go through this branch, right? So then let's talk about now let's label our voltages. This is positive, this is negative. The current is flowing like this. There's no voltage drops over here, by the way. We'll study them to figure it out, but we want to know that this voltage is V0, because if you go up V0, you're going to go down V0, stuff like that. Now, even though there's no current going through this branch, our goal is to figure out the charge, which means I need to know the voltage across the capacitor. So we want to look at the voltage here and here if there were any current. There's no current, so it doesn't really matter what orientation you put the voltage in. Now, because the I is 0 here, right, and V equals IR, that means the drop on this guy is 0 volts, right? Because if the V is 0, then the I is 0. The R is not 0, right? So that means the voltage drop here is 0. So if I look at this loop, right, V0 minus the voltage across this capacitor plus 0 has to add to 0. This has to be V0 as well, okay? And that's because the loop has to add up to 0. So go up V0, down V0, down 0, and we got to end back at 0 again, okay? So that's how KVL works. So that means eventually, after a long time, the charge is going to be C0 V0. So you put a line here, C0 V0, and then it's going to exponentially approach it, like that. Okay. Now, in terms of the current through each resistor as a function of time, we want to figure out how the current is going to look in terms of this. Okay. So let's look at when it's open, right? So let's go back to this case where it's open right now. When it's open, right now, the state of the circuit is this is 0 volts and there's no current flowing anywhere, right? Because the current would come from the battery, but there's nowhere to go. All the currents start at 0 in both cases, right? So it's going to start at 0 current. through R1 and R2. Now, when you close it immediately, so this is the key thing you want to think about. The voltage can't change instantly on the capacitor, but the current absolutely can. So we're going to leave it. So right now we're studying immediately after you close the switch, right? We're going to jump up, okay? So what's going to happen, we close the switch. So now we have current that's going to come out here. And we're not saying the current can't go through here. The current absolutely can go through here. So current's going to come in here, and it's going to split into this direction and then recombine over here, right? So then the voltage drop here is V0. This is 0 volts. There's a voltage drop here as well. Okay, now, because this is V0, if you look at this loop, because you drop 0, it's uncharged, then this has to be V0 because this loop needs to add up to 0. And then this loop also needs to add up to 0, right? And notice once it closed, this 0 loop always is just going to be like, this is always going to be V0. So when it comes to, let's see, R1 is bigger than R2. So if we look at the current that's going to go through here, right? The current that's going to be here is going to be I1 is going to be V0 over R1. And then this current here, I2, is going to be V0 divided by R2. This is immediately after we close the switch. So we close the switch. Because R1 is bigger, it's going to start at a lower current, right? So this is going to be V0 over R1. And and then we'll use a different color. And then this is going to be V0 over R2. Now, as time goes on, this current is eventually going to decay to 0 because this guy's in series with this capacitor. So as we continue, this current, if you wait a long time, this is going to go to 0. So therefore, this guy has to decay to 0. Starts here, and then he's going to decay to 0. But this guy, because he's going to say V0 the whole time, because this loop is going to be true regardless of what happens here. This loop is still going to be true. This is still going to be V0, so he's going to have a constant voltage like that. Let's see. Yeah. Okay. So that is that's that one. Circuit is constructed using a 1.5 volt battery, an 80 microfarad capacitor, resistors R1 150 and 100. Switch is closed, allowing the capacitor to fully charge. Switch is then open, allowing the capacitor to discharge. The time it takes to charge the capacitor to 50% is the time constant here, and we want to discharge it this time. What correctly relates to two time intervals? Well, our time constant is RC, right? So the longer the time constant, the longer times to change. So we have to think about what the time constants are in each situation. So I'm going to erase all this and think about just the R and the C that's seen. So when we close the switch, the capacitor is being charged through this resistor. Like the path goes like this to charge this capacitor. So the time constant in the first scenario for charging is R1C0. When we're discharging, so when we open it, so now it's completely charged, and now the capacitor is going to discharge through a path like this because there's going to be some charge on here, some voltage here. So there's going to be some current that flows through here. It's going to go through R1 and R2 to discharge. Those are in series, so T2 is going to be R1 plus R2 times C0. So this has a bigger time constant. This is bigger time constant, which means it's going to be slower to discharge because the more the time constant is, the longer it takes. So we'll say TD is greater than TC, and it's because it has a larger time constant. And you would show those time constants over here as our justification. Okay. Is the calculate current through resistor R2 immediately after the switch is calculate the current through R2 immediately after the switch is open. So R2 so we're going through this case where we fully charge this capacitor. So this long time we said the capacitor fully charges to V0. That's what we said. So this is going to be V0. Okay, now this is what I'm drawing on here right now is right after the switch opens. Okay, it's not like this voltage stays that way the whole time, but right after the switch opens, the voltage cannot change immediately, right? And so then the current is going to flow out through here and here. Now, there's a couple ways you can think about it. You can say, well, these two are in series, because any current going through here is going to go through here. It can't go through this branch because there's an open path here. There's nowhere for the current to go. So this branch doesn't have any current when we're discharging. So the current is just going to be, so the total voltage drop is going to be V0 for these guys, and then these two are in series. So you just say V0 over R1 plus R2. And you can calculate it numerically because they told you it was 1.5 volts. They told you R1 was 150 and R2 was 100. So that's going to be 1.5 divided by 250, and I get 6 milliamps, or it was 0.006 amps, 6 milliamps. Is the current through resistor R2 increasing, decreasing, or constant immediately after the switch is opened? So once the switch is opened, we're having the charge, well, it's going to decrease because eventually it has to go to 0. That's one way to think about it. But the other thing is because the charge is moving from here to here, the charge on the coplates are going to decrease because they're recombining, because you have current flow, you have charge flowing off the capacitor. So as the charge goes down, the voltage goes down. The voltage goes down. The current through the resistors go down. So it's going to be decreasing. Calculate energy stored in the capacitor immediately after the switch is opened. Energy stored in the capacitor is 1/2 CV squared. So that's 1/2. They tell us what the capacitance was, 80 microfarad, 80 times 10 to the negative 6. And then the voltage was 1.5 squared immediately after it. Okay, so that's 0.5 times 80 e negative 6 times 1.5 squared. You're going to get 5.6 times 10 to the negative 1, 2, 3, 5, negative 5 joules. Energy dissipated by resistor R1 as the capacitor completely discharges. So there's a couple ways you can do this. You can look at, when you're doing energy, we're going to do the integral of power, right? This is kind of back to our mechanics, unit 3, right? Energy is the integral of the power, which you can do as an integral setup, but the current is exponentially decreasing, so it's kind of one of those things that that may be the easiest way to go about. Actually, this is part 2 of a question. I'm trying to think of. Okay, so I'm going to take a shortcut on this one, but theoretically, all you have to do is solve for the current equation and integrate it. That would work. The problem is that might take a lot of time. So let me kind of show you a slight shortcut on this one. All the energy in the capacitor has to go through these 2 resistors. Okay, so it's because they have the same resistance, or not, sorry, because they're in series, they have the same current going through them. So the power is equal to I times V, which implies that the change in energy over time, the amount of energy is just the current times the voltage times the amount of time. Now, because they're in series, they have this is the same for both resistors. It's the same amount of time. So really, the only difference between the 2 resistors in terms of the amount of energy that's dissipated is really just the voltage drop across them. So you want to think about how those voltage drops compare, right? So if we do this and this, we could say, oh, well, the voltage drop on this guy, okay, if you think about his voltage drop, it's going to be I times R2, and this guy's voltage drop is going to be I times R1. Now, how do those voltage drops compare? Because if I want the power through resistor 1, the voltage drop through 1 is equal to I R1, which is equal to, what did they say R1 was? Well, I think they said it was 150. Yeah, 150. 150 times I. And then the voltage drop across 2 is actually 100 times I. So who has the greater voltage drop is this guy, right? So V1 is actually equal to 1.5 times V2. So he's going to have 1.5 times the amount of energy. So if you think about the energy through resistor 1, it's going to equal 1.5 times the energy through resistor 2, because they're in series like that. Hopefully that part makes sense. Now, the total energy we're dissipating is 5.6 times 10 to the negative 5, which has to be the energy dissipated by R1 plus R2 by conservation of energy, right? The energy has to be, where does that energy in the capacitor goes? Has to go through those resistors there. So this is because the energy through resistor 1 is 1.5 R2, you can solve for R2 is you get 1 over 1.5. And what is 1 divided by 1.5? I think it's 0.67 ER1. So then you can replace that here and get ER1 plus 0.67 ER1. That equals 5.6 times 10 to the negative 5. And then you can solve for ER1. So this would be like a shortcut to doing this problem. We might do problems later on. So that's going to be 3.36 times 10 to the negative 5 joules. We might do problems where we have to integrate that, but it's not too hard to derive that. I just didn't want to take up too much time on that problem. Okay, because we have more RC circuits to look at. So circuit shown above is composed of an ideal 10-volt battery, 3 resistors and capacitors. Capacitors are initially uncharged, so that means the charge is 0, which implies the voltage is 0, and the switch is now closed. Calculate the current R1 immediately after the switch is closed. Now, immediately means right before the switch closed, all of these had 0 volts across them. That's the first thing you want to do, right, is identify the initial state. Now we close it, so let's look at our current. So the current's going to come out of the battery, going to go through here. You're going to have some go through here, some go through here, some go through here. Because the current doesn't have to be 0 on the capacitor at the initial start, okay? So let's look at the current going through R1 here, okay? Now, this one's like tricky. You got to think about all the voltages that are happening, right? So for example, this guy has a voltage drop from positive to negative. This guy's a voltage drop. This guy already drawn the plus minus signs. This one is plus and minus. We already have the plus and minuses over here. Okay? So, now because these are plus and minuses, this is where it gets tricky. You have to look at the KVL and you have to identify certain things. Now, one of the things I want you to recognize is if you look at doing this loop right here, this has to be 10 volts. Why does it have to be 10? Because you go up 10, you drop a number, and then you drop 0, and you're back. You have to be at 0. So you have to drop 10 volts right here, right? Which means if you do this loop, then this has to be 0 volts, and this has to be 0 volts. And that makes sense, actually, because if you do a loop here, they're parallel. This loop, they need to add to 0. So if this is 0, this has to be 0. And you can see that because they're parallel as well. So you got to think about the loop, right? So how do I get this 10? Is I did a loop over here or this one here. But either way, because there's only no voltage drop here, this has to be 10 in order for that loop to pass. And for that to be 10, these have to be 0. And now you can check all your loops. Any loop you pick, you should add up to 0 by following that convention. So we know that. And so therefore, we now know the resistance. We now know the voltage across R1. We can calculate I1 as V over R. Because I know 2 pieces of information. That's 0.1 amps. Now, switch S has been closed for a long time and the circuit has reached steady state. Calculate the potential difference across R1. So now let's erase what we just drew, because now everything's different. Because if you wait a long time, what that means is there's no current going through these branches over here. So that means when we draw a current, it flows like this and this. All right? So then we have a plus minus, plus minus, plus minus, like that. Okay, so the current is going to then flow like this. Now, these are not necessarily 0 because these things are fully charged. So we don't know what the voltage is. They have some charge on them. We haven't solved for what that charge is or anything like that, so we don't know, but there's some voltage across there. Okay? Now, let's see. We want the potential difference across R1. Now, this is where you can go a couple options. You can just assign variables and do KVL and KCL, but you say like, well, if I want the potential across R1, I might as well collapse these 2 resistors, because that won't affect my ability to study this guy right here, right? So then you could do this, right? And then you have this, you have this 100 ohm. Then these 2 collapse into a single resistor. So we're going to replace these 2 with an equivalent. How do we find that equivalent? Well, we do 1 over 30 plus 1 over 60 is 1 over our equivalent. That adds up to, just use our calculator, 1 divided by 30 plus 1 divided by 60. And if you do 1 divided by that, you should get the R equivalent is 20. So now it's 20 here. So what we've done is we've replaced both of these resistors with a single resistor that's 20 ohms. Okay? Let's redraw our currents. Now, you could collapse them to find the current through here. And then, because I still don't have enough information, right? Like, so I have to look at this. But at least now I know they have the same current going through them. So if you want to just do just a normal KVL, you could say, well, I'm going to call this I, right? And then we say 10 minus, what's the voltage drop? I times 100. What's the voltage drop down there? Minus I times 20. And we're dropping voltage. That has to equal 0. So we have 10 is equal to I times 120. And I is equal to 10 over 120 then. And I'm using the same I for both of them because they're in series now. They have to have the same current. Right? 10 divided by 120 is going to be 0.083 amps, right? So 0.83. And now I know the current, I can now find the voltage, right? So then the V is 0.083 times 100. I get 8.33 volts, okay? Calculate the charge stored in the positive plate of capacitor C2. So at this point, let's go back to our circuit. We know that this is 8.33 volts. Now, because these are in parallel like this and because of our loop rule, these have to add to 10, right? Because we go up 10, we got to drop 8.33. The remaining we got to drop is 1.67 because these two have to add to 10. This is 1.67 volts as well. Now we want the charge stored on this capacitor over here. So now we know, if we want to charge, we got to know what the voltages are. Okay? So now we know the voltage drop from here to here is 1.67 by our loop rule, but we need to know how the voltage drops here individually are because that will tell us what the charge is going to be. Now, one thing we say, because these are in series, we do know they have the same charge, right? So, like, one thing you can do is you could say, like, well, you know, if you look at it, Q equals CV, the voltage drop on the capacitor is Q over C. So it's the same amount of charge, whatever it is. So the voltage drop is Q over C1. This voltage drop is Q over C2. And those have to add to 1.67, right? So you can say Q over C1 plus Q over C2. And it's the same Q has to equal 1.67 volts. Now, this is equivalent to just saying like, oh, find the equivalent of parallel capacitors. That's where that actually derives from. Or sorry, series capacitors. Use the equivalent, 1 over C equivalent, right? And it's the same thing. But, so this is Q times 1 over C1 plus 1 over C2, which we know. So you can solve for Q. You do 1.67 divided by this number right here, and you know C1 and C2. So it's going to be 1.67 divided by 1 divided by 10 microfarads plus 1 divided by 15 microfarads. And I get times 1e6, about 10 times 10 to the negative 6 coulombs, which is 10 microcoulombs, like that. Or you can do it like that. Is the charge stored on capacitor C3 greater than less equal to on capacitor on C2? Well, let's look at the charge. So Q is equal to CV. So we know the capacitor. We actually know the voltage drop across this guy because, again, with this loop right here, this has got to be 1.67 volts, right? Because these three all have to have the same drop. Because if you look at any loop through them, we got to drop 1.67 volts because we know that this is 8.33, right, in steady state. So this is 20 microfarads times 1.67, and that's going to be pretty big. It's going to be 20 times 1. It's going to be 33.3 times 10 to the negative 6 coulombs. So it's going to be greater than. Okay, switch S is then opened. Determine the current through R1 immediately after the switch is open. So now we have all the charges here. We have all these voltages, and we open up the switch. Okay? The resistors can change their currents, but the voltages across the capacitors cannot change instantly. Right? That's our rule. So immediately after the switch is opened, we got to look at the current through R1. Okay? So can any current go through this battery? So the current would be whatever current's coming through the battery. Well, because this is open, there's no current going through here. And if there were some current going through here, we'd have a huge problem because there's no current. We would have an area where current is not flowing, and then all of a sudden a current that is flowing, right? And that would violate our current law. So because there's no current going through the switch, there can't be any current going through here. So that's going to be I of 0. Calculate the current through R2 immediately after the switch is opened. So R2 then has like this part here. Now, we know this is 1.67 volts. So if we look at our loop rule, these are all parallel. So this is also 1.67 still. 1.67, because remember the voltage can't change across the capacitor. So those are all 1.67. So by those loop rules, so we know the voltage across the resistor. We absolutely know how much current is flowing there, right? Voltage over the resistance, 1.67 V over R, or V over I. 1.67 divided by, actually we want the current. Current is V over R. So that's 1.67. And then what is R2 resistance was 30 ohms. Okay, so it's going to be whatever that is. Now we want the potential difference across capacitor C2 as a function of time. If switch S is open at time 0, label the maximum value. So we know it started with the same charge, right? So the maximum value is 10 microcoulombs. And eventually, if you wait a long time, there's going to be no current. And if there's no current, then these are not going to have any, the voltage drops are going to be 0 across all these, right? Because the voltage drops here match whatever the voltage drops here. So if the current through here is 0, then the current through the resistors are going to be 0. And so then we're not going to have any charge left over. So it's just going to decay and discharge all the way down exponentially to 0, like that. So capacitor C3 is replaced with 2 microfarad capacitors connected in series when S is closed and the circuit reaches equilibrium. Switch S is opened at time t equals 0. Okay, so now we're doing the same scenario, except we're changing this with 2 10 microfarads in series. Would the voltage across C2 be the same or above for part E? So this is about the time constant. So we want to know what's the difference when we make them. Actually, we got to think about what the overall capacitance is going to be when you look at this circuit. So when we open the switch, the R is not going to change, and we want to think about our time constant, our RC. Now, you might think C2 doesn't change, but you got to think about the time constants. They're all charging, discharging together. So you got to think of it as collapse. So if you put 2 capacitors in series that are 10, the equivalent, we want to think about the equivalent, is going to be 5 microfarads. You got to do 1 over 10 plus 1 over 10 because they add in series. So we're basically saying we're shrinking this capacitance, and then these are in parallel. Like this doesn't changing, but this is in parallel. So this C3 adds to this branch here. So if you decrease this capacitance, you're decreasing the overall capacitance. So the C goes down, which means it's going to discharge faster. So it's going to it would be below because the RC time constant is smaller. Okay. All right. Let's take a look at another one. Circuit shows consists of a battery of EMF epsilon, resistors 1 and 2, capacitors C1 with C and 2C respectively, and a switch. The switch is initially open and both capacitors are uncharged. So that means the voltages are 0 across the capacitors initially. At time t equals 0, the switch is closed to position A. So right now we do this. So at this moment in time, set up a differential equation. So this is where we're going to use a differential equation to solve the charge in the positive plate of the capacitor as a function of time, then determine the charge Q of t. Express your answer. So we're going to set up the differential equation and solve it. We do know initially the voltage is 0. So that'll be, initially it's good to know. But what we want to do now is we want to say like at any arbitrary time. So we're not talking about right when you close the switch or right when you waited a long time. We're talking about really what is the overall, like at any given moment in time, what is the charge. So what we're going to do is we're going to draw our currents out. So the current's going to flow through here. It's going to split into 2 branches, and then it's going to combine and form over to here. Now we want to look at our voltage drops. So this is epsilon here. This voltage drop, we just put our plus and minus signs here. Okay. So we're now going to say, okay, let's call this current I, and then this is going to be I1 and this is going to be I2 because it's not going to match, right? So this current is going to be the sum of these 2 currents, I1 and I2. So this one is I, which is I1 plus I2. So now what we want to do is do our voltage loop rule. We're going to start, let's just start here. We go up epsilon, so we're going to add epsilon. We're now going to drop. Now we could either go through this loop or this loop, so we'll do this loop here. That'll be minus I1 times R1 times R. Well, actually, they're both resistance R. And then minus, so actually what you could do, sorry, just to make it easier, to make it all in series, because you know each of these is a resistance R, you can collapse them into a single resistor. That would make your life a little bit easier. And that would be a single resistor of R over 2. Okay, so then they'll all be in series and they all have the same current. That's why we optionally will do this collapsing resistors. That's that optional step. So it's going to be I, the current, the full current's going to go through a single resistor, just with a single resistor of R over 2. And that's because they're in parallel, right? So 1 over R plus 1 over R is 2 over R. which is 1 over R equivalent. So if you just flip them both upside down, R over 2 is R equivalent over 1, right? So we have through there, and then minus the current through here, minus the current through the capacitor. Now, when we're talking about the charge in the capacitor, that is the current. We'll just say the current through the minus the voltage across the capacitor, right? Q equals CV. So the voltage is Q over C as that capacitance there. And that has to add to 0. So we did up there, we dropped here, we dropped here. That has to add to 0. Now the current is the rate of change of the is how much charge is being deposited on the capacitor. So this is going to be epsilon minus dq dt times R over 2 minus Q over C is equal to 0. So then this is our differential equation setup. Then we want to solve this differential equation. The way we do this is going to be separation of variables. So we are going to isolate dq dt on one side, because that's the only way you guys know how to solve separation differential equations, Q over C. Let's go ahead and I want to move the C up, right? Well, actually, sorry, I don't want to move the C up. I want to move this over to here and then move the Q down. Yeah. So we're going to make this, multiply this. Actually, I try to make as few variables onto this side as possible. I think we can't avoid this. So we need to divide this thing whole thing over, right? So we get 1 is equal to dq over dt R over 2 over epsilon minus Q over C. But I would like to make this as simple as possible to do the integration. So I'm going to divide the R over 2 over here. Okay, so first I move the dt up, so it's going to be dt on this side. And then I'm going to divide by the R over 2. So that gives you dq over epsilon minus Q over C. And then I want to multiply both sides by C to get rid of this C on the bottom here. Like, you don't have to do this. You could integrate this as it is. But actually, I want to multiply with 1 over C, because I want to multiply by C on the denominator. I want to get rid of this C down here. That way I don't have to deal with the U substitution. I'm trying to simplify the integral over here on the left side, because I have to integrate at one point. So this is going to be dt over RC over 2 is equal to dq over epsilon C minus Q, like this. Okay, so now I'm going to integrate both sides. This one is just a very simple U substitution. It's going to be negative natural log absolute value of epsilon C minus Q. Okay, and then this one is going to just be T over RC over 2 plus a constant is equal negative natural log absolute value of epsilon C minus Q. Multiply through by negative 1. So it's going to be negative T over RC over 2 is equal to natural log absolute value of epsilon C minus Q. We'll put E as the base to get rid of that. Oh, no, we have a plus C here. E is the base, and you can strip away the absolute value sign as long as you just say, this C and this C are confusing. So we're going to call this C X. Okay, CX. So that's going to equal CX e to the negative T over RC over 2. Hopefully this part's okay. This is just sort of like your calculus topic. So hopefully you're good with solving differential separation of variables. So your Q, if you move this over, Q is going to be epsilon C minus or plus CX e to the negative T over RC over 2. Now we have to just find CX, that constant there. We know that at time 0, the charge should be 0, right? Because it's initially uncharged. So that's our initial condition. So 0 is going to be epsilon C plus CX e to the 0, which is 1. So CX is going to be negative epsilon C. So then your Q is going to be epsilon C minus epsilon C e to the minus T over RC over 2. And that should look very similar to what we do a lot of times, is that exponential decay. This is our time constant is RC over 2. And that's because it makes sense because these two resistors were in parallel. Okay, a long time after it's closed, the charge on the positive plate is Q0 and capacitor 2 is uncharged. At time T1, the switch is closed to position B. Determine expression for the total charge a long time after T1. So we have a charge Q0. Okay, so what is Q0, by the way? Because we're going to put our answer in terms of this. That is if you wait a long time, as t goes to infinity, this is going to vanish to 0. We're just going to have epsilon c as our initial charge. Okay, so we're going to have an initial charge epsilon c, and then what's going to happen is you're going to close this switch. So let's kind of combine this again. So this is C, this is 2C. We're closing this. Actually, let's make this still R over 2, single resistor. And so what's going to happen is now this guy's charged. This guy was initially uncharged, but you wait in long enough time, the current is going to be 0. Right? So there's no current flowing through this capacitor or this capacitor. There's no current. The I is going to be 0 in our circuit here. So if you look at the voltage drop to find the charge, right, you're going to have a voltage here, you're going to have a drop here, you can drop here. The drop here is 0 volts because there's no current going through the resistor, right? V equals IR. So if the voltage drops 0, there's no current. No current. These two have to have the same voltage, right? VC1 has to equal VC2 because by the loop rule, right? Because this is going to be 0, so these two voltages must be the same. So capacitor 1, capacitor 2 have the same voltage. Now how does that help me, right? So V1 equals V2. Now the total charge cannot change because the charge has to go somewhere, right? So the total charge has to remain still this amount here. So we know that whatever the charge Q1 plus Q2, it needs to add to Q0, which is epsilon C. Now the voltages on the capacitors are, so we know what's the relationship between the voltages and the current and the charge. Q equals CV. So that means Q1 is equal to CV1 and Q2 is equal to CV2. So that means Q1 over C, and then this is 2C because it's twice the capacitor, has to equal V1, which is equal to V2, which is Q2 over 2C, right? So basically you multiply this by 2C, you get 2Q1 has to equal Q2. So now we can solve for the charge in capacitor 2 because we can say Q1 is equal to 1/2 Q2, and you can plug that into there to get rid of Q1. So we have 1/2 Q2 plus Q2 is equal to epsilon C. So this is 3/2 Q2 is epsilon C. So then Q2 is 2/3 epsilon C. Okay, a long time after T1, the switch is now closed to position A. So we've settled it now, and now we're going to switch it back to A again. Okay, so now we're switching it back to A. And we now know what the charges are going to be because you can actually figure out what Q1 is. Q1 at this time is going to be 1/3 epsilon C because the total has to add to epsilon C. Derive an expression for the current from the battery immediately after the switch is closed to position A. Okay, so now at this point, we've closed this switch and we want the current, but this thing is charged now. How much charge does he have? Or what's his voltage? Well, his charge is 1/3 epsilon C. So his voltage, Q equals CV, because that's the first step, right? Immediately after the switch is closed, the voltage cannot change immediately. So we need to find that voltage. That was Q over C, and that's 1/3 epsilon C over C. So it's 1/3 epsilon. So this is already at 1/3 epsilon right now. Okay? And then again, this thing here is just R over 2, a single resistor. We collapse them. And so what's the voltage drop across this thing? So now the current, sorry, I'm getting ahead of myself. The current goes through here, going to go through here, going to go through here. But if you look at your loop rule here, right, this has to be 2/3 epsilon. Why? Because this goes up epsilon, and we got to drop a whole epsilon down. So now the voltage across there is 2/3 epsilon. So what is immediately after the battery is going to have, well, it's whatever the current through the resistor is, right? So we know the current through the resistor because I know two pieces of information. I know the resistance and the voltage drop. So the current, that's the current through the resistor, which is going to be the current through the battery because they're all in series. But it's going to be V over R, which is 2/3 epsilon divided by R. So it's going to be 2/3 epsilon over R, like that. Okay, and that's because the current through there has to match the current from the battery, right? And so that completes everything we need to know. Determine the I infinity a long time after the switch is closed to position A. The current from the battery? Well, there's no current that's going to go through the capacitor. That's in series with this guy because there's no, this thing's disconnected, right? There's no way there's any current going through here. So current's going to go to 0. Long time. Okay, so that is circuit analysis. Let's do one last problem. I know we've spent a long time. This is a long review because circuits is very complex. Let's look at a current density problem, just so that at least so you see one example of how that works. Cylindrical wire of length L and radius RW carries a steady current. The current density in the wire is not uniform and varies with the radial distance R from the center of the wire according to the function this, where J0 is this constant. The wire is made of a material with resistivity rho. Express all your answers in terms of this. Derive an expression for the total current through the cylindrical wire. So the current is the current density is per area. So we want to integrate J dA to get the total amount of current here. Okay, now the density, because it's a function of a radius, you want to think about how do you want to cut it up? Because the density is changing with radius. You want to pick a region, and you want to pick a ring like this that's very thin. If it's very thin, then the current density is about uniform there, right? So this is thick, this dr. And because it's such a thin ring, the r doesn't vary, right? Like it has an r distance, but it's pretty much constant because it's so thin that we just take the density. So the amount of current going through there, di, is the density, J0, 1 minus r over rw, times the area, right? Times the area. And what's the area of that? Well, that would be like a thin rectangle that's wrapped into a circle. So you take the circumference of that circle times the thickness. And so then to get the total current, you're going to integrate this from little r going from 0 to rw. Okay, so let's pull out everything that's a constant. That's 2 pi J0. Integral from 0 to rw. Distribute the r. It's going to be r minus r squared over rw. dr. And so that's 2 pi. Let's see. Let's do r squared over 2 pi J0. R squared over 2 minus r cubed over 3, big RW, from 0 to RW. Okay? And so that's going to equal 2 pi J0. If you plug in RW, you get RW squared over 2 minus RW cubed over 3 RW. If you plug in 0, you're just going to get 0. So this is 2 pi J0. RW squared, that's going to cancel RW squared. So 1/2 minus 1/3 is 1/6. RW squared, like that. Okay. So that's the total current going through the wire. Determine the potential difference across this wire. Okay. So the potential difference is, I think what I meant to ask here is not exactly the potential difference. So this one, because the current density is not uniform, I didn't mean to ask it across here. Derive an expression for the overall resistance of the wire. Okay. So the overall resistance of the wire doesn't have to do with the current density. This is just making sure you know, we do rho L over A. Right, so what's the length? Let's see, length L, and the radius is RW. So this is going to be rho L over pi RW squared. And that's the overall resistance there. If the same wire was melted down and reformed into a wire with length 2L, determine the new resistance of the wire. So this one's pretty interesting. It's about how is this going to change? Okay, so if you think about what's going to happen is we're going to double the length, right, for sure. But the radius of it, because you're melting it and you're reforming it, the volume has to stay the same. The volume is constant. That's the key thing. So even if I make it twice as long, it can't be the same radius. It's got to be skinnier too. Right? Now, it's not twice. It's the volume is constant. It's not like you just say like, well, you have it, you double the radius. What happens is the volume of a cylinder is pi r squared times the length. Right? And so if we are going to double this, then r squared has to go down times 1/2. Okay, so r squared is going to be 1/2. So the r is going to go down by 1 squared 2, but the area is just going to go down by 1/2. So it's going to be times rw squared over 2, like this. So this is going to be 4. If you flip that, times 1 dividing by 1/2 is times 2. It's going to be 4 rho L over pi rw squared. And so what you see is going to be 4 times as much. It's going to be 4 times as much. when you do that, because not only is it getting skinnier, it's also getting longer. Okay.